Okay, this is David Zierler, director of the Caltech Heritage Project. It's Friday, September 9th, 2022. It's great to be back with Professor Michael Gurnis. Mike, once again, it's great to be with you. Thanks so much.
You're very welcome, David. Yeah.
Mike, what I want to do today is pick up the story in the late 1990s. I've already heard from Jeroen Trump in his discussions with people like Steve Koonin about the need to really increase the computational capabilities at Caltech. So prior to that, in the 4 or 5 years prior to that, in the late 1990s, from your perspective, where was the Seismolab computationally? Where was it doing things, and where were your interests in terms of those computational needs that were already met, and where did you see serious need for growth?
Yeah, so that's a good set of questions there. So let's see, in the late 1990s, so that was a period in which most, I would say, most of the faculty, except me, um, their computational needs were met with sort of fairly large servers that we had actually in the Seismolab itself. Okay, so we're already fairly far into this whole idea of these Unix workstations, probably more than a decade, I suppose. Uh, and most of the work was being done, I would say, on those workstations itself, for most of the seismology faculty. Um, but for me, things were still, they just weren't there. They just weren't enough. And we had already, from, let's say, the mid 1990s to about the end of the 1990s, we had actually moved into a time when we actually had our codes, the stuff that I did in geodynamics using the finite element method. We had things that actually scaled on parallel computers, right? And so we were using, it's all a little bit hazy, each particular year, but Caltech had, I don't know exactly what, I think just before just before I arrived and this computer existed, Caltech had what was called the Intel Delta on campus. So after parallel computing was invented at Caltech in in like 1983 or 85 or 84, 85, something like that. Maybe. Um, we people could do quite a bit. And because of Caltech's lead in this particular area, um, Intel donated first what was called the Intel Delta, which I actually never used, right? And so that was sort of in the early 90s. And then that was up, and that was the fastest computer in the world, I think, or at least at a university campus, and Caltech had it. And then it was the Intel Paragon. And these used the Hypercube architecture, and Intel Corporation wanted to, get involved with this because it was their chips basically which were running it. So they figured, well, big computer needed a lot of Intel chips. And they built several of them. They were just basically very large versions of the computers which were built at Caltech or in several companies which eventually folded. And so I was able to use those machines. And then somehow in that period of time, I think they were supported by NSF, but I forget the actual details. We had some very large HP supercomputers on campus, right? And interestingly enough, these were national facilities, I think. So at Caltech, for a period of time, competed in this arena of supplying or hosting basically one of some of these big pieces of iron, big iron. It was called big iron, and I was already sort of used to using these sort of facilities. First, when I was a postdoc, we talked about that earlier. When I went down, when the San Diego Supercomputer Center was one of these facilities, and then when I was at Michigan, I continued to use these facilities, and then I continued to do this sort of at Caltech. But no, I mean, we basically had sort of tapped out. I actually even used some of these workstations that the other faculty were using. And there was one paper in particular in that mid '90s area that I wrote with Shiji Zong, that's Zong, mm-hmm. And I don't know if you spoke with him or not, but did you?
I have not yet.
Oh, okay. So any event, we these actually didn't scale on big parallel computers, but see, we would put this is when we first introduced faults into the codes, but we would just run for like, I remember there was an article in Science magazine, I think it was 1995, so it's a little bit earlier, but it sets the context of what you're saying. And so there was like 5 runs in this paper, and each one took 5 weeks to compute. So we had one big, really nice workstation with, at the time, a lot of memory. And we actually, for that one paper, it just ran solid for 9 months, I believe, for that paper. But then anyways, this other code then became available, which was called Sitcom, CITCOM, which was originally written by Louis Moresi. And he got it to, there was a distributed way of before MPI became available, of distributing this on a set of workstations. It wasn't very efficient. It was overwhelmed by communication costs. And then Shiji took the code and he introduced this thing called MPI, okay, which then suddenly became the de facto standard in parallel computing, and largely is to this day, and was basically a rewrite at Argonne of the cubic, I forget the actual spelling of it, cubics, which was the original message passing language written at Caltech for parallel computers. And so we were able to start using this software, but we were also able to use one of these in-house machines with a different piece of software, but that actually used shared memory. It was a different kind of a model for parallel computing. Anyways, we were all set. Now with Sitcom, we basically needed a bigger computer, right? But the amounts of parallel computers that were available out there, even with the NSF systems, was not there. Okay, but now, interestingly enough, this guy, I forget what his name is. Hold it. I think his name was Tom Sterling. Hold on. Anyways, it was a real book, and he called it the Beowulf, right? He invented this, and he was a staff member in CACR, the Center for Advanced Computer Research. And I think I mentioned this program last time, and they brought in this guy Paul Messina, and they brought him in from Argonne National Laboratory to run CACR. And one of the people they brought in as a staff scientist, I think his name was Tom Sterling, and he basically came up with this concept that you could take all of these workstations and put them together with an Ethernet, use message passing, and build your own homegrown supercomputer, right? And so Jeroen and I wanted to do this. So I already had gone through all my startup money, but Jeroen and I got on an earlier mode of computing. He and I pooled our resources in the Seismo Lab, and we joined up with some other faculty members, and just for an equipment grant, right? But then when we got the money, the computing paradigm had changed so much between when we wrote the proposal and when we got the money that and we had the Caltech money too, pooling our resources, we decided, well, we were going to build our own Beowulf, right?
Yeah.
So what we did is, we basically figured out how to do this. I forget how many processors we actually had, but he and I set up an assembly line in the computer room of South Mud. So interestingly enough, before I arrived, I don't know what year it started in, but from the 1970s, on the second floor of South Mud, we had a giant machine room, right? And we still sort of had it, but people kept carving it back, right? As workstations and supercomputers got more powerful and a little bit smaller, the room got smaller, and they took space away from but it had a raised computer floor. You could put wires under it, lots of air conditioning. It was a real thing that you would go to a university computer center. But the Seismo Lab had its own, right? But because of things which had happened over the previous time, the seismic network operations and the computing for that and the staff members kept growing, right? Competing almost with Trinet and Terrascope and all that kind of stuff. So it got squeezed. And then Jeroen and I wanted to build up a computer again all of a sudden because the paradigm had changed. So we basically bought all the parts, right? And we bought really good parts. Like we made sure we spent more money on the fans. And these basically were going to be desk side computers, right? And we built this thing. We set up assembly line. We had it operating there for about 2 weeks, and our graduate students and postdocs would serve time on the assembly line, and it would go down the assembly line. And we built, I don't know how many, maybe 200 workstations. There was 100. There's probably more. Maybe Jeroen remembers it. There's probably even something written about it. I don't remember. But then we went to Home Depot or something like that. Maybe it didn't exist at the time. And we bought all these warehouse shelving units, right? And then we assembled it. We assembled it in there too. And actually, I even got a pinched nerve because I was working in there building all the stuff, right? Assembling all of this with wrenches, and we built it all. And and then it was kind of interesting. There was 2 rows, and on the 2 outer faces, you just see on each side, there'd be like 100 or so. And so that meant 200 processors because we had dual processors in each box, and the lights would flash and everything. But on the back side, which was the covered part, basically we have all the wires. And so we bought, all these routers on the inside, and all the Ethernets were connected and stuff like that together. And of course, there originally was a window there too on the outside. We covered all that up just for air conditioning. systematics. And this was great. I mean, immediately we started, the two of us, Jeroen and I, what we did is on one side, this is what we did. So on the original one side, we said, well, we'd run sitcom, and on the other side would run SpecFem, right? But what we'd really do, of course, is, okay, we'd do sitcom or we'd do a SpecFem back and forth or whatever, depending upon what the students and postdocs really needed, right? And we got some really big calculations done with SpecFem and with sitcom. But and then so there's two things that sort of emerged from this collaboration. Okay, one was, first of all, well, the Seismolab needed its own big supercomputer, so we had gutted our room. We wanted a bigger room, and that's going to be one theme I'm going to talk to you about. But then the other thing we needed is that we were now running all of this high performance computing with a lot of people. And what we needed to do is we needed to develop software in a more modern way. Let me talk to you about that first, okay?
Mike, if we can go back just for a second, in the 1980s with parallel computing, why was that relevant to you? Why was that a special form of computation that was good for what you were after?
Well, initially it wasn't. I mean, well, okay. First of all, the reason why it was very important, and I used this picture last time in the video, because when we wrote the first paper in parallel computing and geophysics, I showed you we took a domain and we broke that domain up, right? Well, it's just a natural way to imagine how to solve a spatially continuous domain in which you have naturally put it into subdomains with something like a mesh or elements or something like this, right? So, I mean, even when you think about what happened, if you go back to when the von Neumann machine was first invented during World War II, and when Johnny von Neumann brought it and built one at Princeton, what they would do is, of course, they had this finite difference methodology, right? And the finite difference methodology was that, well, you broke your domain up into a bunch of little subdomains, right? Well, then that naturally gives rise to the concept, well, if I want to make things faster and faster, then what I want to do is I want to break my domain up into smaller domains and compute all of those simultaneously. And now this is very interesting because different equations and the way that they're formulated in a computational way are solved in different ways. Some things are inherently just naturally parallel, right? Is that there's no connection between anything spatially, and all you can take 1,000 processors and subdomain it up, and you can make it 1,000 times faster, right? If you use 1,000 little computers that are all work simultaneously, and then you combine your results at the end or whatever. Now, most domains, right, and this is, I'm going to use seismic wave propagation, and it contrasts with mantle convection because the equations are quite different. In seismic wave propagation, everything is naturally, all the interactions are local, right? So even the way that the equations are solved, all the interactions are local. You have a wave here, and it suddenly interacts with the surrounding domain and how the wave affects the displacement and pressure around you. That's actually really quite different from the problem I solve. It's called Stokes flow, in which, interestingly enough, the whole problem is actually always globally interconnected, right? If you move it over here, it instantaneously has an effect over there, right? And so some things could naturally move over to a parallel computer, like seismic wave propagation, whereas the Stokes flow remained quite difficult. And the way we solve that is we actually create a global a matrix that actually represents the solution of the whole kind of problem. And you have to sort of invert the matrix at every moment in time, in physical time. And so, and the big breakthrough in that happened in the Seismo lab with Louis Moresi, who is my postdoc, and he invented in what's called an iterative method, right? So you take this big matrix, and in some sense, different parts of the matrix are put onto different computers, and they're solved simultaneously. Now, the thing about this, and with the big thing about parallel computing, is that it's always a balance between how much local computing you do and how much communication you do, both local communication as well as global communication, right? And so, but Louis seemed to have cracked the nut, right? At about this time in the early 1990s, where we could now, even though we are still sort of setting up, but we never naturally set up the global problem, we still actually have broken up our mesh into subdomains, but we're doing a lot of computing locally, and we're doing a lot of communications. That's why this word that is now, why this word called HPC, high performance communications and computing, HPC, yeah. HPCC, high performance computing and communications. Why it's very, very important is because you have to communicate and you have to compute, right? And some things work well and some things didn't work well. Mantle convection is probably one of the worst, most difficult problems to solve, but we've cracked it, actually. It took a lot of work initially. So in any event, because we could crack that nut, right? Well, we needed now we could do it, right? We wanted a big computer so we could actually do it.
Mike, what would be an example of a research problem where you need the big computer in order to actually get the answers you're looking for?
Well, both seismic wave propagation and mantle convection are great examples of that. They're classical problems in science and in geophysics that both require a gigantic computer. And so, I mean, we just knew that it's a big problem right from day one. I mean, we knew even the day I got involved with this, well, this is a toy problem. We've eliminated all the interesting physics from this particular problem so we could squeeze it in onto this computer, right? And then eventually we reached a point where, we would do bigger and bigger problems on what we call the von Neumann machine, right? So most computers, even this Mac, probably what you're on too, is still what we call a von Neumann machine, right? And so the big breakthrough happened, of course, in the 1983 at Caltech when they invented the concurrent computer, the hypercube computer. Now there are different models of how that's done these days.
Now, Mike, the paradigm shift in the late 1990s, what was that? What were you referring to?
The paradigm shift basically, well, we knew that we could now compute it, right? Well, we did the math, we did the computer code, but we didn't have the computer. We didn't have the hardware, right? So what we needed is we needed the hardware. And because an individual PC was so cheap, see, there's the whole thing. It was the Beowulf paradigm that allowed us to jump forward on this. And it was only a small window of time where the individuals knew they could race ahead because computers had become very cheap because they became a commodity, right? That's the interesting thing. Before this, big supercomputers were extremely expensive. It was dominated by initially several, but by the mid-90s or the early 90s, just one company was left standing, right? And that was Cray Computer. And each one of these computers was so expensive, and there were so few of them. I mean, mostly they were used at the weapons laboratory at the Department of Energy, Los Alamos and Lawrence Livermore, as well as the oil companies to process seismic data. Those were the two big users of computing before, also in weather prediction. Those were the three big things. Oil, which was geophysics, making atomic weapons, and the other one was weather prediction. They all needed big Cray computers, right? But then what happened is we had the PC, which of course changed the world, but then this idea of the Beowulf came up, right? That concept was invented at Caltech. And that means because computers individually were so cheap, you could go to the computer store and buy this stuff and then put them all together with an Ethernet. Suddenly, you could make a computer for $100,000, which was just as powerful as a Cray supercomputer was, for $5 million, right? And, if you had a bunch of cheap labor, AKA graduate students, right? And you had a soldering iron, and a couple of wrenchers, you could build one of these things. So Jeroen and I built it. And then that's the hardware paradigm shift that actually happened, right? But then is that, oh my gosh, we want to build a bigger computer, right? And so Steve Koonin was still at Caltech. So Steve Koonin, he was a very good provost, in my opinion. He only stayed 5 years in the particular job. But the reason why he was good in this area of science is because he understood this and recognized this, right? He knew the power of computational science, right? He was deeply involved with the weapons laboratories, right? And so he knew, how important these big supercomputers were. And he knew, of course, what we did at Caltech. And so we needed to build a bigger computer. We knew, and he was through areas in mechanics and in other areas of physics. He sort of got the general idea of what we did in geophysics. So he bought into this idea. And so the division chairman at the time, Ed Stolper, convinced the provost or whatever to renovate the sub-basement of South Mud. Now that floor was in the control of the Seismolab. So the whole floor, it was giant real estate down there, was still in the control of the Seismolab. But it turns out a vast area was occupied by microfilm. We had all these film chips. It was one of 3 or 4 laboratories in the country in which we stored all these seismic records from what was called WWSN, the Worldwide Standardized Seismic Network, which was put in place by, I guess, the U.S. Air Force to monitor nuclear explosions from the Soviets. And that's what paid for the Seismolab before I got around. But in any event, and so anyways, we basically agreed we'd give up this space, right? And so we had to figure out where to get this film chips. And later, through some people outside of Caltech, we got a bad reputation.
Mike,
they're foaming at the mouth. I am sure you interviewed people who want to put my neck in a noose, but it wasn't my fault. It was Helmerger and Kanamori, and who are observational seismologists, but they still want to string me up. But in any event, we had this idea because we wanted to move forward, right? And so we were going to build this big. Then Jeroen and I basically at that time, what we had thought we were going to do is, okay, Mike, well, we built one for 200. We will put our resources together and we will build 1,000 processor. We will do it ourselves. We will just build this thing, right?
Now, Mike,
we convinced with the Caltech had to do it. What Caltech needed to do is they needed to throw the resources in, right? They needed to throw the resources in to build a big computer room again, right? And basically what we were asking them to do is build what a university would usually build for the university, right? A huge computer center but we wanted one in the Seismo lab, right? Okay, so we built this thing, and it got and then suddenly, guess what? Well, now we have to find the money to build this supercomputer, right? We built the computer room, the infrastructure, the air conditioning and the electrical, a massive amount of electrical power is required, right, to build this thing. So we built it. This huge room, right? Clean, beautiful floors, lighting. You go in there, air is moving around, but empty, right? Okay, so now private enterprise, being the United States, is not going to let this Beowulf whole paradigm get in the way of making a lot of money, right? So what happened is that the workstation vendors, Dell Computer, Compaq, even Intel tried this out, but that was sort of an earlier generation with the Delta and the Paragon, and also IBM. They all were going to get involved with this, right? So now they were going to take this and they were going to build these computers. Okay, so are we going to build it ourselves? We're going to find a little startup company to build it. Some people now were making a transition that they weren't going to build it, but they would buy one from a startup. And there's a whole bunch of little startups around the country building these. They were compute clusters, right? So this is really before the big data farms and Google took the universe over, but it's basically very similar to all of that. But so in any event, these companies got involved. So anyways, I remember we got involved with Dell. I have no idea how initially Dell Computer got involved, but there was this guy, I can't remember his last name, but Jeroen had his last name. His first name was George, right? He worked for Dell Computer Company, and we brought him to Caltech. Jeroen and I brought him down to the computer room, right? And he saw this bloody thing. Holy smokes. First of all, he knew that we were at the bleeding edge of software, right? And then there was this gigantic empty computer room. And one of the big problems that Dell was having is it was trying to sell these gigantic, in terms of footprint, these were giant computers, right? I mean, they were like 50 feet long, right? They would take up, like half the size of a house. And no one had any space for these things. So Dell wanted to make these things. No one had any space for any of these things. So universities had all these big these computer centers all around the country, but no one had any footprint, right? No one had an empty computer room in the country. And he came here, he says, holy smokes, we can put a Dell computer in here. And I have no idea what happened, but through hook or crook, and Caltech, and they will remain secret, and they're not, through a non-disclosure agreement, Caltech bought a gigantic Dell computer of the same size that the national supercomputer centers were putting for everyone in the country. And the Seismo have it its own. And it was like 1,000 processor Dell Super. It was their largest state of the art. It ended up on the list of one of the fastest computers in the country for a couple of months. And they put it in there, and we just went to town on this thing. It was like, we were running the sitcom program. Jeroen was running the SpecFam and whatnot. And so, yeah, that was like incredible, right? But of course, the rest of the country caught on. And, within like a year, all of a sudden we needed to upgrade the system, and we eventually got an upgrade. But now all of a sudden, of course, they wanted money, right? More and more money. They wanted millions and millions of dollars where to pony up. And we did get another NSF proposal funded, right? But then when we went back to the trough, we would just get slammed down. We got so annihilated a couple of years later because it was like the jealousy was just dripping from the reviews. Why does Caltech, this geophysics, why are they going to get the thing that the whole country needs and they get to have it all by themselves? Bad proposal, bad proposal. Even though we had one great science question after another, and we're the only ones in the country who had the software, it was just, everyone knew this was the future, and why should one department have it all, right? So it became kind of like it was kind of like that was like the end of that.
Mike, had you known Jeroen? Did you work with him before he got to Caltech?
So yes, of course. I mean, he and I are just about. I'm a little bit old. I'm a couple of years older than he is, but I met Jeroen because he and I were Packard Fellows,
right,
at the same time, right? And we met in Monterey, probably. I think no, I actually met Jeroen even before I came to Caltech. I went to Harvard to give a symposium, and he and I met, and then we talked there, and it was interesting. Initially, we didn't hit it off because I was already totally infatuated by high performance computing, and Jeroen had not yet, right? Jeroen's claim to fame before he got to Caltech was by refining a theory called normal mode theory of using that to go directly from seismic data to large scale earth structure, right? And he was a long period seismologist, sort of like Hero, although he actually had an earlier career even before that. That is Hero. And Jeroen, of course, was a master mathematician and the use of mathematical methods. And he was not a computational guy. And it only was when he got to Caltech, and I forget when that was. Let's see, I came 94. I think we tried to get him in 96 or 97 or something like that. It took a while, took a couple of years.
And were you involved in the recruitment that Ed Stolper was leading?
Yeah, so eventually, yeah, I was maybe I was the chairman of the committee. I don't really know. But initially it didn't work. We wrote our report and the faculty, approved it, and we made him an offer, and it was a little bit difficult. And then Ed basically sat on it for a while, and he was conniving. Ed was really good at this, of convincing people to come to Caltech. But yeah, I mean, eventually it was very unusual, to be honest with you, within the division, because, I mean, first the committee did all its work like we normally did, and then the division voted on it, and then he eventually actually turned us down. It just sat in sort of limbo. But then at some point, Ed just used his own discretion and just figured out he could hire him, and he did. And he did. But so that was great. And
Mike,
and immediately we started to hit it. I mean, one thing that Jeroen and I did was this, right? It was all the hardware stuff, and we saw the connection. But interesting enough, there was a parallel intellectual thread. So, and this parallel intellectual thread was that so this was really quite interesting. I'm going to go back. I had, because we had invented this new software at Caltech, I submitted a regular geophysics proposal to NSF, and it was the use of the big finite element codes. And basically, because of that, we could actually do very, very fine scale things at the same time. We could do coarse things, right? And it went to NSF, and presumably it did very well in geophysics. But it was kind of funny. I got the program manager called me up on the telephone, and she says, "Mike, something very interesting happened." Her name is Robin Reichland. She was really important for both Jeroen and myself and to geophysics overall and other people in the Seismo lab. But she calls up, it was something really funny happened, Mike. So I had someone from computational science. They invented a new program. It was called KDI. Apparently Al Gore, when he was vice president, came up with this program. It was something like knowledge and discovery informatics. I don't know what the heck it was. It was just an NSF program, but it was totally run by the computer scientists, right? And apparently a program manager, went to Robin Reichland and she said, let's look at your proposal. Let's see if there are any proposals in there that computer science can fund. That's very unusual. So they went through their proposals and he goes, wow, look at this one. So they picked my proposal out of the pile. And she said, Mike, you're going to fund your proposal right away. And I'm not even going to pay for it in geophysics. Anyways, that was really cool. But then, interesting enough, 2 years later, NSF decided to create another program. And they're going to call it ITR, Information Technology Research. And these needed to be interdisciplinary proposals, right? And so I already was involved with this CACR, the Center for Advanced Computer Research, right? And so I went, I think, this is interesting. I think I and Jeroen by ourselves, or maybe other people in geophysics, we put something in, right? And we got trashed, right? And so then we went over and I talked to Paul Messina, right? Who is the director of CACR. Says, Paul, we want to play in this game. How do you think you can help us out, right? So there was another guy, his name was Jim Poole. He was a mathematician who was, the deputy director, and he and I got along really quite well. I got along really well with Paul too. Anyways, there was another guy about my Jeroen and I's age. His name was Michael Avasis. And he was a staff member over there. He was a former physicist. He was brought in to CACR to help with computing. But Michael was using this thing. He was doing two things. He was doing stuff in Python. And I didn't know what Python was. On the one hand, because I had just learned yet another language called Perl. I didn't think I really was ever going to learn another thing called Python. And then there was something called frameworks, right? And this is all interesting stuff. And so, but the other thing that Michael really was big on was he was really big on software engineering, right? And so what we did is we teamed up with Michael and with Jim Poole, and Paul gave us his blessing, and we wrote a totally different proposal. What we proposed to do here is we were going to do two things. Well, actually, sort of like three things. We were going to, we were going to bring software engineering into geophysics. We're going to train them. They would use repositories, use best practices. For our graduates, we would train them, right, in this area. Number one, no one ever talked about this. No one talked about this in geophysics at the time. Number two, we were actually going to then put our codes, SpecFem and Sitcom. SpecFem was written in Fortran. Sitcom would be written in C. We're going to put them within frameworks, and we're going to put them underneath this object-oriented system within Python, and they would be objects within a framework, and different things could be shared. They could share information with one another. And we would do this individually within SpecFem and Sitcom. And then we would also try to bring Sitcom and Sitcom together. Jeroen and I did this. We got a huge amount of money at the time, right? And so we got postdoc, paid Michael's salaries, graduate students. And we were training. And so our software, just went skyrocket forward. No one in geophysics was using Python. No one. And no one was doing frameworks or anything. And so we just ran ahead for several years, and we did this, right? And we learned so much to do this. Eventually, Python took science over. Starting at around in the early aughts, I think it probably really exploded. But then another thing was happening simultaneously within geophysics. The community writ large, mostly in my field of geodynamics, but sort of geophysics, and also with the encouragement of the National Science Foundation, they wanted to create a national center for geodynamics in the US, right? They thought that it had reached its point, that it needed to move forward. But no one liked this idea. Everyone liked the idea because it was big, to move up to the next level of bigger science, maybe more funding. But on the other hand, people also, and earlier this idea had floated around, and partly a reason it floated around within geodynamics is, I don't think I ever mentioned this to you, but starting about 1980, I think the first one was in 85. I went the first one in 86. We spent part of our summers at Los Alamos. And this was the way we were going to solve the access to computer issue, right? But simultaneously within that, NSF then generated the supercomputer centers. But nevertheless, it was such a cool program that people around the country would gather in Los Alamos, nominally for 2 weeks, but a lot of students would come for the whole summer. Is because at the time, Los Alamos within computing still had this auger like sense. It was still, I don't use the word glowing in a good sense, in the sense that, they just took off with computing, right? Of course, it was all behind a fence. And I would go there in the 80s and the early 90s. I don't know when the last time I ever went there. And it developed an extraordinary sense of community and sharing. And we were way in geodynamics and mantle convection. We were way ahead of the whole community in benchmarking and validating our codes and doing intercode comparisons and all kinds of things like that. That started in the 80s. But the only reason I bring this up is I've lost the thread. Unfortunately, of why I came back to Los Alamos and from Jeroen and benchmarking. I forget.
Their computing powers were even bigger than what you had built at Caltech?
Well, yeah, behind the fence. Sheesh. Yeah, they had, but we were doing a different paradigm. They had Cray computers, and eventually they got involved with this as well. But in any event, we needed to have bigger computers. Oh, this is software engineering. Oh, that's right. Software engineering. Oh, yeah, that's right. I know why I was onto that thread. It actually was because of the sense of the community. And a whole group of people around the country in my field, and there was about a half a dozen of them, professors at the top universities, myself, Brad Hager at MIT, Rick O'Connell at Harvard, Peter Olson at Johns Hopkins. They're all behind this idea to build a center in geodynamics, right? But no one wanted it. No one wanted it because we were still arguing about the equations and how to formulate a problem. And all these breakthroughs were being made, in some sense, at the graduate student faculty BI level, right? We don't know anyone to guide our research. And I remember I came out, I was really strongly against this. especially in the 1980s, I just came out very strong. No, we don't need a center within geodynamics. This is going to undermine creativity. But nevertheless, we knew where supercomputing was going, right? We knew everything was getting bigger, and we better get bigger, even though we knew we still had to do this competitive way of doing highly creative science. So they all wanted a science center, right? They wanted a science center, but no one wanted to give up their science. So we were going to have a powwow. Sorry, I know that's probably not politically correct anymore. At Johns Hopkins, it would be a one-day powwow. People would fly in. And so all these people individually came in to Johns Hopkins and had this meeting around the table about how we were going to do it and who would be the PI and stuff like that. Okay, well, if this was Jeroen's idea, and it actually created some bad blood within the community that I then spent the next 6 months trying to. Well, Jeroen was not in geodynamics, right? But Jeroen and I ourselves, but the community overall, had made this big leap forward. What we needed was not a center for science. We needed a center for software. And we knew what it was, software engineering. That's really what we needed.
To keep up with the hardware, because the hardware was already ahead?
To keep up with everything, to move the software forward so we can have bigger, more robust software, right? And take advantage of all the hardware changes, right? And also to do more benchmarking and validation and things like that. We knew the future was not one of a science center, but the one in which it would be an infrastructure center for software, right? So, but the rest of the community no one was talking about this, right? So interestingly enough, Jeroen, myself, and Michael Levasis, we showed up all together at this meeting. And everyone had already put a proposal in to have it at Harvard, MIT, okay, a science center, right? And we came onto the table and we said, nope, what the community needs is software engineering. And then Jeroen and I brought Michael Levasis, who was incredibly articulate about this particular topic. Right?
Where was Levasis at that point?
Caltech. He was at the Center for Advanced Computer Research, right? And so he could articulate that what we really needed to make this big breakthrough was engineering. And guess who had already got this giant NSF grant and have all this experience in-house in the Seismological Lab was us.
That's great.
And everyone around the table was like, well, first of all, yes, absolutely, instantly, everyone knew that this was the solution of the problem. In fact, the reason why we had the powwow is because no one, everyone was an equal player and everyone wanted it, right? But no one wanted to give up anything, right? But no one had any experience in software. And then suddenly we showed up with a person who could articulate this and a whole team of individuals who knew exactly what they were doing. And it was like the biggest deflation. But then also it was, and actually, and then there was like a voting around the table and everyone voted. Caltech only got one vote. And of course it was unanimous. But the feelings were because they felt that we were disingenuous, because how could we compete, right? Well, I could have found a person at my university too and brought a person there. They weren't working with these people, right? Yeah, and then actually, so then it was decided, okay, Gurnis, you're in charge now. You have the next year to orchestrate the whole community and make a center for the community and then give it to the National Science Foundation.
What did you think of the prospects before you got started?
I didn't necessarily really want to do this. being the prospect of us getting this.
Yeah.
I was confident. Jeroen was totally confident. He says, Mike, you're going to go there and you're going to blow them out of the water and you'll be in charge. I didn't really want to be in charge. These were all my friends, you know?
Yeah.
Sheesh. And so, yeah, so then they loved it. NSF loved it. And then, so I then spent, and I actually had to fly, you know, and then I actually had this like, you know, on a peace mission, literally to Cambridge, Massachusetts, a couple of months later. But again, it would be at Caltech. There would be a center, and NSF would support it, and it would be done with staff members, but would have all this, you know, whatever, would have this all these committees that the community would have complete oversight on. And even though I'd be director, I'd have these committees, an executive committee and steering committee. Well, this was worked out in the proposal process, and there was a proposal writing team. And we put the proposal together, and we sent it to the National Science Foundation. They went out for 12 reviews, and they got 12 excellence back.
What were the key points in the proposal? What was most important to convey?
Software engineering,
yeah,
frameworks, community building, benchmarking. It was all the things, except the community building. It was all the things that Jeroen and I had all this experience on,
yeah.
Right? And we knew all the words to say because Michael Levasis, you know, he was what was called our chief software architect, right? That's what he became. He was the chief software architect. And that was really quite interesting. And this is really quite interesting. Here's another interesting aspect that happened at this time. So I was I was not the associate director of the Seismological Lab. I had previously been, right? And, but one thing we had, and that was actually immaterial. And the only reason I knew this is because, you know, I had already been in charge of the facilities of the lab and everything. And we had these other places. And the Seismological Lab still at the time had the Kresge Laboratory. We had our own campus up above the Rose Bowl. And so I knew it all. I knew all the space and the building and everything like that. And we put together an internal proposal at Caltech that we would, so Jeroen and I put this together. So he and I worked on it. So I worked with the National Science Foundation. And on this particular aspect, because it then would be sort of be part of the Seismological Lab, right? That this thing which emerged, which, and immediately, even at this time, I knew what was the future. So I instantly got like the domain geodynamics.org, right? Even though we wouldn't use it for a whole another year later. And so we were going to build it in the Seismological Lab facilities. Well, we had no room, and I already went through the whole space crunch here because we had just built this giant supercomputer facility in the basement, and Dell Computer put a supercomputer there. And, you know, the seismic network had expanded beyond our wildest dreams, and we had no space. But we had the old site, we have our new seismological laboratory. But the director controlled the old seismological laboratory. And so we went back and we said, we want to renovate the facilities. And we would do several different things. We would house CIG, what eventually became the Computational Infrastructure for Geodynamics, CIG. Unfortunately, it's a bad acronym. But in any event, and it was designed on purpose, so to take the science out of it. Mm-hmm. So in any event, we had this facility. Says, we want to renovate the Kresge lab, right? And I'm sure you've seen pictures of it and stuff like that. I mean, this is where in the cellar of that was this long thing for one of the Benioff strain meters was actually in that hillside, actually. The older one, the mansion, actually had already been sold, but this was built from a grant specifically for the part of the Seismological Laboratory. And so we proposed that we're going to renovate this whole facility, right? And we would do several things. Not only would we house this NSF center up there, right? The other thing we would do is we would make it like a conference facility. It's in a beautiful neighborhood, right? Unfortunately, it ended up being 3 McMansions in a little road, which eventually it became when Caltech sold it. But the unfortunate thing that happened is that the administration didn't really like the idea, and a person on the division's oversight committee, I forget what it was called at the time, Sean Solomon, who eventually became the director of the Lamont Doherty Earth Observatory. And Sean didn't like the idea. He didn't think it was good to take scientists and cloister them away off campus, because one of the key things is for people to interact, especially with mathematicians and computer scientists.
I mean, isn't this the whole reason the mansion was relocated to South Mud?
Well, it was one of the reasons why. That was one of the intellectual arguments. But I think one of the arguments was made is they didn't like the Seismolab being so independent. Mm-hmm. And so they wanted to put it under their arms as sort of like a control thing by the division chairman, I think. Those are the 2 reasons, intellectual as well as control. The division wanted to control the Seismolab because the Seismolab was more powerful than the division. And that's always been a problem, except, the division has gotten so big at this point. I don't think it's not an issue anymore. But even when I first came here, it was an issue. It was an issue with even having a director of the lab, because he would be, or in earlier times, they viewed he would be more powerful than the chairman, and they didn't like that. And that's, there's certain things I don't want to talk about. But in any event, so one of the problems that happened is suddenly the provost, and I think it was Koonin, realized that the Seismolab had this really incredible piece of real estate off campus. So, holy smokes! I had no idea Caltech had this place, the Seismolab, and it's controlled by the director of the Seismolab. It's like, I used to go up there because it was part of our facilities, right? And there were certain rules that I had to exercise. But in any event, and so it says, holy, and now we don't really want to cloister you up there, but here, all this real estate, let's sell it. Oh, crap. What a pain in the neck. So somehow the division chairman and the provost and the director at the time, which was Jeroen, had this idea that they were going to sell Kresge, right? Well, this was before real estate went so out of control, it was beyond the pale, right? And so they sold it, right? And they divided up the money. I think the provost took half the money, and then they gave the other half to the Seismolab as an endowment fund. Well, it's been a pretty good endowment fund for me. It's one of the few resources that I have. But I'm bitter that they didn't give me all of it, right? It would have been much better. It wasn't, it was ours.
And was Hiro still director at this point?
Oh, no, Jeroen was director.
Jeroen was director.
This happened, I'm pretty sure, when Jeroen was director. Because he and I were scheming all the time, I'm sorry, about the future of geophysics in the United States. But here's the laughable thing, this whole thing, that they would put us here on campus. But of course, we still had no space. But guess what happened in the same year? Well, Caltech suddenly bought they bought the St. Luke Hospital in North Pasadena. Did you know this?
I knew this, yes.
It's still there. It's owned by a real estate developer who can't develop it. Caltech bought it for $10 million. And Steve, I think it was Steve, had the bright idea they were going to create this thing. I think, look the history up. I think it was called CCIT, the Caltech Center for integrated technology, CCO, integrated technology. It's going to be a technology hub, right? And we would have a North Campus, right? So my desire to open a NSF center on campus, in which the director of the Seismological Lab at the time, Jeroen, had no space for, and they took the space we wanted to use away from us. In one case, oh no, you can't be off campus because you'll be isolated. Oh, let's put you off campus because now we've got this gigantic campus. And so they had two tenants of it eventually up there, right? And they had what was going to become the big telescope that was going to be the 30-meter telescope, and myself were relocated up there. So the 30-meter telescope was put in the church or the religious compound, and I was put in the medical building, and we took a floor out, a part of that floor, and basically it was like being in commercial real estate. And I was up there I had my office here, and I did my research program here, but this center I ran for NSF for more than 5 years. It was a facility off campus, and it was a stunning success. I got the thing going from 0 to 60. The community absolutely loved it. And
Mike, what happened there? What were the research projects?
Well, we did everything. We had a whole team of half a dozen software engineers up there, and then we basically took over the software development for mantle convection, for seismology, for it was all a collaboration. We had the engineers there, and then we worked with people all around the country. And we basically we divided ourselves through my idea. What we're going to divide ourselves up into is we had like these different working groups. We had mantle convection. We had what was called short-term tectonics, which was earthquakes and things like that. And we had long-term tectonics, which is like mountain building and things like that. Then we had seismology. And we also tried to develop the Earth's geomagnetic field, okay? And I was nurturing that. And so we built all these things, and we had working groups, and we basically did exactly what the NSF wanted to. We brought software engineering to the community, this really successful center. It's incredibly successful today and just grows. But what happened, several things happened. Well, in its last year at Caltech, it actually moved to CACR. Because CACR, was not that involved with it, was a much smaller self, and there was some space over there. But then Caltech decided to sell it, right? No one on campus wanted to go up. Well, how did the 30-meter telescope and geophysics know it was not going to be a success, right? I mean, this thing is happening all over the country. It's been going on since the 1960s, right? People have been building research campuses, and they build these arms, right? And the whole idea was, and actually David Terrell was the czar of it, but in the end it was a czar of nothing. So and actually the interesting thing is, because I was actually on a campus, Caltech charged the full overhead rate on this, right? And they pulled in a lot of overhead on that grant. And so they renovated this area. It was very, very successful. But then they wanted to get rid of it because no one wanted to go up there. So then Caltech sold it. But when did they sell it? When real estate was really high. So some numbskull, bought the property for more than $30 million. Caltech made a $20 million profit on it.
This was before 2008, 2009, I assume, when the market crashed. Or it was more recent?
No, it was, I mean, I'd have to go and see when I was director of this thing. I was director of this. It's on my CV. Let's see. Yeah. So yeah, actually, just by looking at my CV, probably will tell me. Sorry. Uh, Let me just tell you. Interesting question. So when did I ended up finish being director of this thing? Um, being and I'll director. Oh, up to 2010. So what happened is, but I was 2010, but we were on campus at that time. So a couple of years before that, I don't know what happened. Caltech was going to sell it, so we wanted to sort of move out. Um, and uh, but then the other thing that happened, what year was that? Um, so Jeroen left Caltech, unfortunately, and maybe it was like 2007 and 2008. So just around that collapse there, right? Then what happened is they didn't know who they were going to make director of the Seismolab. So they had an acting director for quite some time, right? I was really, really busy. And then the chairman basically came to me and he go, Mike, I need you to become the director of the Seismolab.
And this was Stolper?
No, this was now Ken Farley.
Uh-huh.
And Ken said, Mike, you've got to take over, right? I mean, they needed someone really prominent in the field, and they needed someone, at this point, I guess they presumed they needed someone with a lot of management, but I think it was more prominence in the field. And so I don't really want to do this. But then I decided, well, if I gave up CIG, right, even though I made it, right, I made it to what I had the idea. Well, it was a collaboration with Jeroen. That's what the community needed. He didn't understand geodynamics. He was totally bought in with me on software engineering and software. But in terms of the culture of my community, I had those two aspects of it. It was the negative and the positive, and Jeroen only saw the positive. Right? Negative being my community did not want a science center, but it wanted something. Mm-hmm. But I also saw the benefit of software engineering. And so Jeroen and I had this series of students and other folks we trained. So we were totally bought in. We were gaga all about it. So Jeroen left, and there was a long period in there without a regular director. And eventually, after a long time, I accepted Ken's offers. But what I would do is I said, I'm going to have to pull back, and I'll help the community move forward. And so I announced to the community that we're going to have during this. So we were actually then up, and I would have to help write the proposal and I was on the writing committee because it's all done by the community. Even though I was director, we even appointed a chairman of the writing committee, even though at the time I was going to be PI. So when it was all being written, I was going to be the PI of this. It was a big group of people. I don't know who the hell they were. I can't remember. But, and so we were writing this proposal, and then right near the end, it says, you know what? We're gonna have to find a new director here, right? So then the community did that, and appointed a person. Her name, she's now deceased. Her name was Louise Kellogg, who was in this field, and they would move. Some activities would stay on campus. It would move up to the University of California at Davis. That's right, Davis. So, and now it's going like gangbusters, right? And so the proposal came back and reviewed based upon its past accomplishments, mostly, and I take credit for those with the community. There's excellence all across the board yet again, right? But yeah, I have to admit, sometimes people don't really understand why suddenly I was not the director after a while, right? Because things were going so well. And it succeeded after that, right? So it kind of looks weird, in my opinion. It says, oh, well, I became director of the Seismolab, right? Because I was passionate about the Seismolab, and I knew it needed a director. And even though I was not a seismologist, but I remember I went and I was very close to Don Helmberger. And I remember he and I were talking all the time about different things, but almost always about science, right? And I go, Don, what do you think I should do? I'm not a seismologist. In the typical way of Helmberger, he looks out the window and stares out the window for a long time, like he always did. Then he looked at me and he just burst out laughing. And he goes, Mike, Don Anderson wasn't a seismologist either. I can't believe he said that, because he was really one of the giants of seismology.
What do you think he meant by that?
What he meant by that is, for the last 20 years, Don wasn't a seismologist. In fact, he was more like me. We were putting together things. We were synthesizing how the Earth worked. We were leading the community. We weren't just an observational seismologist. And at the time, Don hadn't been, right? I mean, since probably the I don't know what year, sometime definitely by the late 70s, Don Anderson was not leading observational seismology anymore, right? He was a big ideas person within the community, extremely influential, right? But yet, so he said that being a seismologist was not a prerequisite to being director of the Seismo Lab. That's basically, what our core observational seismologist said. That was his view, right?
But isn't the move from the mansion to South Mud, isn't one of the bigger stories there that
geophysics?
Yeah, that's it. That it's more than seismology. It's now sort of geophysics. Right,
but it already made that transition because Tom Ahrens had been hired by I forget what year he came in on, but what year did Tom start? I know he was up there, up at the Kresge lab. There was a big explosion one time and they blew out one of the labs of the lab up there. I don't know if you ever heard about that.
No, I did not.
Just a rough memory, but I don't remember the story, and there's no one around anymore who can remember that. I mean, maybe Bob Lieberman at Stony Brook might remember that.
So I just looked it up. He got
somehow
Tom Ahrens got to Caltech in '67.
Well, there you go, right? And we had not, the South Mud hadn't even been designed yet. But Tom, I think, had built some stuff already up there in one of the labs, right? But because he was up there, they were going to design a major component of the South Mud building for a next bigger light gas gun, right? And interestingly enough, I remember Tom telling me, I think it was Tom telling me a story. And it must have been already when he was at Caltech and he would become quite prominent in the field of mineral physics, because they were trying, when they were going to, I forget what the green building. So I'm not really sure if I've got this right. Maybe part of the reason why this building I'm in was built the way it was in reaction to the green building at MIT. I don't know if there's anyone, do you know this building?
I know the green building. I don't know if there was a connection in how South Mud was built,
though. So if you see a picture of MIT, like an iconic picture of MIT is a picture from the Charles River on a beautiful sunny day, which never exists there, across the beautiful blue Charles River with all these sailboats, and you see MIT, and then you get this building right in the middle, and you got these radar domes on the top. It's this little teeny little skyscraper like zip that goes up there, right? That's the green building. And the green building is an absolute abomination for science and collaborative science, because there could only be a couple of professors on each floor, right? And it just totally segregated things. So then all of a sudden, Caltech was going to build its new geophysics building, and Clarence Allen took the lead. And so sort of in reaction to the green building, they were going to build the South Mud building here on our university campus, and it was going to be just the opposite. It was going to be totally level, the ability for everyone to interact with one another. So this staircase in particular was designed to be completely open, right? So people would see each other from one floor to the next, could start talking and even have discussions there. And the hallways were wide, so everyone could have discussions in the hallways. And of course, our seminar rooms and our coffee room were all built for everyone to come walking around and talking with one another. And so I think it was in reaction. If you, one of the old guys, I mean, older than me, that you're probably interviewing, you should ask that question if they know about that.
Okay.
And probably, I don't know who, probably Aaron's probably told me that story. I bet you it was Aaron's, because he told me a story one time when I think MIT was trying to hire him away from Caltech, and he was having a hard time thinking about how they're going to mount this gun in the green building, and somehow it was going to be shot up vertically, and it was kind of crazy. Yeah, Tom was an interesting scientist.
Mike, the last topic I want to touch on today, I want to go back to the computer, the 200 computers that you built with Jeroen. First, let's start with the name. Why Beowulf? What does that mean?
Well, I think Beowulf is from, what is it, Nordic mythology?
I think so, yeah.
Just look, it's like a small little scruffy guy goes up against, it doesn't Beowulf fight Gilgamesh fights him in some big sword fight or something like that.
Uh-huh.
And it's one of these David and Goliath stories. And Beowulf it's a story. I mean, Beowulf, I think, is a story, but I think it's a story of an underdog after a big guy. So it actually was discussed, and I think it was, and again, it's another Caltech story, much more than a Seismolab story. Although the biggest, I mean, the computer. I don't know if I got the names right. I mean, you probably already remember. I got a bad memory. Beowulf cluster, Wikipedia. So actually, it says here on the web. Oh yeah, well they attribute it to NASA. Okay, well, so the name Beowulf referred to a specific computer built in 1994 by Tom Sterling and somebody else at NASA, but presumably it's NASA. It was NASA JPL. Blah 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 blah. Geez, there's a lot of stuff about MIT in there, but he was at Caltech for a long time. Geez, it's interesting. The world keeps changing so much. But he got the Gordon Bell Prize in 2007. Let's see. I wonder if they even listed who gave the Beowulf. That's interesting. Anyways, again, it's because of the name Beowulf comes from the Old English epic poem of the same name. So it's an epic poem, and again, it's a little guy who can. And so what we did, I mean, it just filters into this idea that, we just rolled up our sleeves, spent, I know it was a lot of money, $100,000, but we went and we got a multi-million-dollar computer, right? Effectively, if we were going to buy it from Cray Computer. And so that's why it's the underdog. That's why it's called Beowulf, yeah. And I think we built the biggest one at Caltech.
How long did it take, soup to nuts, to get it up and running?
I don't know, several months, I guess, at least. I mean, Jeroen did a lot of research on what parts to buy. or no, he delegated it. Jeroen was a great delegator. He delegated it to someone else, but he was very careful to make sure you spent a lot of money on the fans. That sounds crazy, right? But because just so air moved, right? Because we don't want this thing breaking all the time. And yeah, and there's pictures, I guess, of it. I mean, I used to never come in the office and take pictures, but I'm sure there's some pictures of us assembling this thing and pictures of the computer. But it was fun. Yeah. I don't know. It was several months to actually do it.
And did you see this technology as sort of the updated version of parallel computing? Was it parallel
No,
computing?
it was specifically for parallel computing.
It was.
Oh, it was for parallel, period. I mean, this was like, because we built a high-speed interconnect, right? We bought a system from an internet provider who does from Cisco system or something to make it go very fast. This was definitely in our calculations, and it was probably one of the most expensive parts of the computer. It wasn't the Ethernet cables. It was this box from Cisco systems, right? That actually could transfer the message passing from one computer to the next very, very quickly. And so, yeah, it was, yeah.
What was an example of a particular research project or question that now was answerable either more efficiently or answerable, period?
Well, one of the things that we were doing at the time, I'd have to actually look at what papers were run on this computer. So this would be from the early 90s. But it was sort of, what I wanted to do is take sitcom, and we wanted to run it with the detailed material properties of the mantle, right? And it just took a lot of computer power, right? And so that was one thing that we were doing. The other thing that we were doing, and this is in line with the connection between SpecFem and Sitcom, is that we also wanted to do a lot of seismic calculations simultaneously. Because now, one of the things that we had pioneered at the time, and it was very powerful, was to take our models of the mantle and do the kind of stuff that Don Helmberger did with the synthetic seismogram, except do it for millions of seismograms. And so there were several papers in there in which we combined seismology and the geodynamic models in this sort of way. And yeah, all the students. Yeah, it's kind of interesting why I would necessarily forget but I sort of just forget like which not always, but sometimes I just forget which stuff was run on which computers, because so many things happen over time.
Did it?
Yeah. So one thing that happened now, like here's an important breakthrough I had, and it actually gets back to this thing I said KDI stuff with it. So I had a student, Magali Billen, became a prominent professor at UC Davis, and Magali used one of the versions of Sitcom on these parallel computers, and again she put in all these intense variable viscosity or material properties, because that's what makes plate tectonics different from just fluid dynamical convection, right? There are all these intense material properties. And now what we wanted to do is we wanted to scale it up into 3D. So Magali a lot of her work was done actually on these big parallel computers that we built in-house. Yeah.
Did this system convert some of the faculty and students in the Seismo Lab? Did they see what was possible now as a result of having this?
Well, a lot of people left and they built little miniature versions of what we had here, that's for sure. But no, I mean, the software basically required, both SpecFem and Sitcom in particular, required computers like this, right? So, we may have been first and we talked about it, but it was quickly forgotten that Caltech, led in parallel computing, right? So simultaneously with the work that Jeroen and I had done, there was another student, and he was in the Seismo Lab as a postdoc, although he got his PhD degree. His name is Brad Agard. So it's like, did you come across that name?
I have not yet.
It was a student of Tom Heaton. Well, anyways, Brad actually was a student of Tom, but Brad became an expert in finite element analysis. So it's AAGARD or something like that. So, it's one of these Finnish things, lots of A's in it and stuff like that. So anyways, Brad Agard was doing something. He was not really that close to Jeroen and I at the time, but he also was using parallel computers. He was mostly using, probably, the Intel machines and other variants. And eventually, I guess he did probably use the Beowulf here. But they actually ran the first 3D dynamic simulations of earthquakes, right? The area that Nadia Lapusta, the current faculty member, has come to dominate. But before, maybe when she was a graduate student or whatever, Brad was doing these things at Caltech with Tom Heaton, right? And so that's another big example of big parallel computing. So in all these different areas, so dynamic rupture, mantle convection, tectonal physics, regular seismic wave propagation, all of our students realized, or a large fraction of them, that large scale computing was required for a lot of people, but not for everyone, right? Because interestingly enough, the some of the work that Don Helmberger's students would do would not be that computationally intensive, but we would take it and we would make it computationally intensive, right? With students, they made it with lateral variations in seismic properties, and then we would want to do millions of calculations simultaneously with Don's codes, with other students and things like that. So, yeah, I know it was just, everyone knew, computing and geophysics have gone hand in hand ever since, the early 1960s, right? Always, and even before we got our hands on supercomputers, one of the big uses within the country before the NSF supercomputer centers was the oil industry for seismic processing, right? So the big three things in the country, in the 1960s and probably in like the 1970s was making atomic weapons, predicting the weather, and finding oil with seismology.
The Holy Trinity.
Yeah, there you go.
Mike, in our next talk, I'd like to pick up on when you first got the sense that Jeroen Trump was going to leave and what that would mean for you.